defaults. Okay, entropy coding, inverse entropy coding, which covers information theory, VLC, Huffman arithmetic. We have a little bit left. Okay, so we're gonna finish up this guy, and then we move on to quantization. Okay, and if we have some time, we're gonna start going into the prediction, transformation, decorrelation part. Okay, then we're gonna connect everything together. Hopefully, it will make sense. Okay, so that's the goal. Okay. Now, before, let's do a quick review. So where were we? We were at arithmetic coding. Okay, and I want to revisit this example really, really quick. Okay, this is adaptive arithmetic coding. This is how state-of-the-art entropy coding is right now being implemented in practice. This exact algorithm is what being used in practice nowadays. So, and as you can see, it's very adaptive, right? We did not make any assumptions on the behavior of the symbols or anything like that. Automatically, we keep track of the frequency, the occurring frequency of the symbols, and let the arithmetic codes figure itself out. Okay. So as you can see, in the beginning, since we don't know any information about A, B, and C, the sensible thing to do would be assume that they are equally likely, right? So 1/3 for A, 1/3 for B, 1/3 for C, and that's how we get this assignment. And instead of putting 0.33, 0.66 here, I put 33%, 66% because I'll need those percentage later on. Okay, you can go back and figure out exactly the numbers that you are supposed to put here. Okay, later on. Now, and if you receive B, then you update your table. Okay, and since now with this current state table, B is twice more likely to happen comparing to A or C. So likewise, it will get allocated a longer length. Okay, so that's how the allocation in the second step is quite different from the allocation from the first. And as you can see, B now has a much larger interval. Okay, so then you can figure out what is the lower bound of the interval, the upper bound of the interval, so on and so forth. The next guy you receive is C, so you will update the table, and then you do the allocation accordingly. Okay, so this guy get 2/5, this guy get another 2/5, this guy get only 1/5. Okay, that's how I get 0, 20%, and then 40% here, and another 40% there. So as you can see, the more you let this algorithm run, the more it will converge to the true occurring frequency of the symbols. Okay, but it demonstrates a very important properties of arithmetic coding, which is the size of the interval is roughly the product of all the probabilities of occurring of the symbols that you observe. The size of the interval, okay, is roughly the same as the product of all the probabilities of occurring of the symbols. Okay, that is very important because from here we can see that each symbols of probability P of X contributes log base 2 of P of Xi to the output. See, with much larger intervals, we have the freedom to pick a nice binary number to transmit to the other side. So we don't need to spend a lot of bits to describe. But when the interval getting smaller and smaller and smaller and smaller, you need a lot of resolution for the final number to send over, right? And that's where you have to spend a lot of bits. Okay, so arithmetic coding, if you take a look at this from this very hand-waving viewpoint, actually approaches entropy if you let it run for a long time. Okay, so it's this arithmetic code can be proven to be near optimal. Okay, with even with finite precision arithmetic, okay, because a whole number of bits or bytes must be sent to the other side. Okay, we rarely send. Usually we round it off to bytes, and then we send it to the other side. We don't send like 2 bits, okay, or 2.5 bits, right? So that's why it's not exactly optimal, because of practical implementations. And then there are other implementation issues which we don't have time to talk about. But in practice, you probably prefer integer implementations. You don't want to multiply by things like 0.3333. Okay, it's very difficult to represent such a number in using the computer, right? We want nice integers number, for example, and then we would like something to have incremental output, right? You don't want to wait until everything happens and then start sending the numbers over. Okay, you start sending bits over along the way when you encode. Okay, so in practice, we never wait until the end of the symbol string to send a number over. Okay, we start sending these number over. We start sending these bits over along the way when we go along with the coding scheme. Okay, so I'll let you figure that problem out. Okay, another thing with arithmetic coding is that this scheme is very sensible is extremely sensitive to error. Right? If our communication channel has error, we're in big time trouble. Suppose that this bit, instead of being 1 and it's turned to 0, all bets are off, right? There's nothing we can do. Unicode if this guy becomes 0, okay, it gets flipped to 0. Everything behind is basically garbage. You just have to throw them away. Okay, so it needs a lot of resynchronization. So basically, after you let it run for a while, you stop and then you start fresh. Okay, so that's create a synchronization point so that if you make a mistake here, at least you only have to throw away this much of information, not the entire string from now until the end of time, right? So those are practical issues that we have to that distinguish the toy example that we have versus the way arithmetic coding is implemented in practice. Okay? Now, today let's finish up run length coding. And the main idea is this, okay? We will try to encode long runs of a single symbol by the length of the run. Okay? Now, so this is also a lossless coding scheme, and this is our first attempt at inter-symbol coding. Inter-symbol means you actually take a look at your neighbor and try to make a decision, okay? Up until this point, even with arithmetic coding, we never take a look at the neighbor, right? The only thing we know about the neighbor, the only thing that allows us to go on is the frequency bit, right? How many times something happens, right? But we never care about our neighbor. Agree? Okay, so here, this is our first effort at trying to do something that involves the neighbor, right? Suppose that you have a long runs of 0. Okay, 0, 0, 0, 0, 0, 0, 0. Okay, it would be pointless to encode 0, then encode another 0, encode another 0, encode another 0, right? Especially if we know that that is very based on Jones and Min's lectures. We know that when we design good transform, we're gonna try to have as many 0 coefficients as possible, right? The entire idea about having a good transform is being able to approximate something with only a few non-zero coefficients, correct? Everything else should be 0, right? So we're gonna encounter a situation where we have a long string of 0. And if you have to encode a long string of 0, one guys after another, you're gonna run out of bit rates very, very quickly, right? So let's try doing this thing. And it's best to illustrate by an example. This is actually a block that I copied out from the JPEG coder. Okay? As you can see, let's count, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12 symbols here, 14 zeros here, another ones here, that's 13 plus 14 plus 37, and you come up with 64. So that's a typical 8 by 8 block. Okay? A typical 8 by 8 block that you just yank out of JPEG. And it's typically, with a good transform, with a good quantizer, we're going to see something like this. Okay? So you see strings of zeros, right? 2 0 here, 1 0 here, 1, 2, 3, 4, 5 zeros here, 14 0 here, 37 zeros there. And we're going to try to take those long runs away. Okay? So this is how JPEG recommends doing this. Okay? You encode, you translate the sequence into another sequence of symbols. Just like we're grouping 0, 1 to yesterday into another symbols, or in the homework assignment, we group two guys into a newer symbols, right? We can do the same thing, okay? And the way we form the newer symbols is this. We're going to encode the size of the values, okay? Which means how many bits we need to encode that numbers, and then the run length before it. Okay. So for example, this is the number of consecutive zeros before the current non-zero symbols. For example, if I'm at 5, this run length will be 2. Okay, because I have 2 0 in front of me. If I'm at -3, the run will be 1. Okay. If I'm 1, the run will be 5, so on and so forth. Okay. And the size here is the number of bits needed to encode this current non-zero symbol, okay? And then followed by the amplitude of the exact value, okay? We need to transmit the value over, correct? So, using this example, I'm going to be able to do this, okay? The first symbols that I have will be 0, 4, 14, okay? Why 0? I'm the first, right? I don't have any 0 in front of me. So it's 0. Why 4? You need 4 bits to describe 14. Correct? Okay? Now, we have to be careful too because we have to deal with the sign. Okay? But let's delay it for 1 minute and it will be clear, right? So 0, 4, 14. And then guess who's going to come up next? Can somebody read out the next symbol for me?
2, 3, 5.
2, 3, 5. 2, 3, 5. Correct? 2, 3, 5. Okay? Because I have 2, 0 in front of me, I need 3 bits to describe 5. Okay? What is the next guy? 1, 2, negative 3. Okay? I need 2 bits to describe. Let's just think about the amplitude only, the absolute value only. Okay? So I need 2 bits to represent 3. Okay? And then I need 5, 1, 1. I need 5, 1, 1. Okay? To describe this guy. And then I need 14. Right? 1, negative 1. Correct? And then what would you suggest me to do with these 37? Yeah, right. 0, 0, 0 or something like that. Okay? And it turns out that this is a spatial symbol because it's at the end of the string. So this indicates this is the end of this block. Okay, so this is the end of block symbols in JPEG. Okay, 0, 0 here. This is a spatial symbol. So this is it. This is our new sequence of symbols. Okay, and we're going to feed this through Huffman and arithmetic coding. Okay, we're going to feed this through Huffman and arithmetic coding. We don't feed these. Okay, so this is how run length coding is being done. Now, let's talk a little bit about the binary values that follow the run length and the size. Okay, so the binary values that describe 14, 5, negative 3, 1, so on and so forth has this form. You need a sign bit, right? Because it can be negative. The coefficient can be negative. Okay, and then you need the most significant bit all the way to the least significant bit. Right? Now this most significant bit, you never have to do anything interesting because it's always 1. Correct? The most significant bit of anything, especially when you have variable length like that, will always be 1. Okay? Okay, for example, 5 would be 101. Correct? It's always 1. So you don't need to encode this, but you need to encode the rest. Okay? And in a sense, what I'm trying to do is just exactly this. This is the table lookup. Okay? If you have 1, you actually, if you have 1, then all you need to encode is positive values, right? Which is 0. If it's negative 1, you need right here. Okay? And we don't have any most significant bit, least significant bit to deal with. Okay? So only this. So as you can see, this is simply a table lookup operation. Okay? If it's, let's take 4 as an example. Okay? 4 as an example. How do I get 0, 0, 0? First, my sign bit is 0. Okay? And then I have 1, 0, 0. But the most significant bits, I don't need to encode, right? So I only have 0, 0, which is here and here. Okay? And if you continue going on, you're going to be able to expand this table and being able to see this is a one-to-one mapping. This is a one-to-one mapping. There's no confusion whatsoever. Okay? I can always go from here back to here or from here to here. Okay? Or, well, you figure it out. Okay, first you need a 0, and then 14 is what? 8 plus 4 plus 2, right? Okay? But you don't need the first significant bit of 8. You only need 4 and 2. Okay? So, if you want to do it by formula, this is the formula. This is the formula. This is how we binarize. We translate number to binary. Okay? This is one way of doing it. So if I do encode this, these guys, okay, are raw binary. They get encoded like this. Okay? And then these guys will go through Huffman or arithmetic coding. Okay? Now, we don't pass these raw binary into Huffman and arithmetic coder because they behave in a pretty much random fashion. They're just, okay? These are the values of the coefficients. And most of the time, if you have a good transform up front, there's just not much that I can do to predict the behavior of the coefficients. Okay? So that's why we just do raw binary here, and we only encode Huffman and arithmetic, these symbols, because they actually have some redundancy effects. Okay? So this is how we do run next coding, and that finishes up the lossless coding part. Okay? From now on, we're going to start with the Q box. Okay? So we will try to investigate this lossy operator. Okay? This operator allows us to throw away information and trade off with the reconstruction quality versus bit rate. Okay, so we finish this part, and we're going to start talking about quantization here. So entropy coding techniques perform lossless coding, but it doesn't have any flexibility in trading off. Okay. You are hoping to be lucky, that's all. And in practice, with images we saw yesterday, like Lena and Barbara, so on and so forth, even those Glasgow frames, the maximum you can do with lossless coding is roughly around 2 to 1. No more. 2 to 1. Okay? Because it's a very tight constraint, right? We have to be able to recover exactly what's being fed in. So there's just not much flexibility. Now, quantization is a lossy, nonlinear mapping operations, okay, that throw away information, and it has the two main applications for quantization is A to D conversion is one, and then compression is the other. Yes. Questions? Okay. So this is how a quantizer works. Okay. This is the Q box, which is at the encoder. At the encoder. Okay. X is the input coming in. It lives in the real space. Okay. So typically, and then the output is typically in the integer space, or binary space, or some finite precision space. Okay. So the forward quantizer is basically a mapping technique. Okay. If you happen to be from here to here, if you live in this space in the R line, okay, you get mapped to this quantization step size, which is 100. So if you are from xi minus 1 to xi, okay, then the output will be 1, 0, 0. Okay? Okay, so here I put binary, but you can imagine you can translate that to decimal if you want. Okay? So this is called a quantization cell, or a quantization bin, or a quantization interval. Okay? And you get translated to here. Okay? So the mathematical operation is this. Okay? When x belongs to that interval, then y, the output y is just yi. Okay? Now, the size of the interval is called the quantization step size. Okay? And this is extremely important because it's the step size determines the amount of information that you'll be throwing away, right? If you have a large quantization step size, you would imagine that there's a lot of confusion, right? At the decoder, it knows that, okay, the original symbols live somewhere in there, but it doesn't know exactly where it is, correct? Okay? So it will have to try to estimate it somehow, okay? And that's the goal of the inverse quantizer. So this is called the quantization level, or sometimes we call it code word. And this is the clipping or overflow region where you might be running out of space. Okay. Now in compression, we almost never run into this situation because we can always find out what is the maximum. We have an input that is range limited, right? So we always know the behavior of our maximum coefficients and our minimum coefficients. Okay, so we will be able to design the quantizer appropriately. Okay, this is mainly a problem in A to D conversion, for example, where you don't have you don't know the range of your input beforehand. Okay, so that can be solved. Now, the inverse quantizer is doing this. Okay, so intuitively, the inverse quantizer receive the y, which is, for example, this guy here. Okay, and it will figure out that so the original guys live somewhere in this neighborhood, right? It will live somewhere in this neighborhood. Okay, but exactly how do you reconstruct the x hat? You have to make a guess, right? You don't have any other information. You just have to make a guess. What is a sensible thing to do? What is a reasonable thing to do? Put it in the middle, right? Why putting it in the middle? Why not just here? Putting it in the middle warranty the lowest max error. Okay? But I cannot make any other statement. Okay? It turns out that in a few minutes we're going to find out all the behavior of the quantizer, and we'll be able to prove certain interesting properties, right? It turns out that the reconstruction actually depends on the behavior of the PDF. If it's uniform, then we put it in the middle. But if it's heavily biased one side, then we shift our reconstruction that way because it's the sensible thing to do. It's reasonable. Okay, and we can prove that mathematically, showing that to minimize the mean square error of the reconstruction between x hat and x, okay? If we know the PDF of x, we will be able to put the reconstruction at the centroid, okay, of the PDF region. So that we're gonna attack that problem in a few minutes. But right now, let's just say we put it in the middle and see how the behavior of the quantizer, okay? So if I put it in the middle, the typical reconstruction would be this, right? X hat of I is, and this is exactly the middle of xi and xi minus 1. Okay? So that's how I get all of those red dots. I just put it in the middle. So this is if you put Q, you follow by Q inverse. Okay, by the way, which is a tremendous abuse of notation, right? There's nothing inverse about that. Okay? What that means is, for any given interval, you map it to some guy in the interval. Okay? And this is called the error of the quantizer. Okay? Okay, the difference between x and x hat is the error. Okay, so quantization error is x hat minus x. Okay, what is the maximum quantization error? Can somebody tell me the maximum quantization error in this case? Delta over 2. Delta over 2. Right? I cannot make more error than that. Maximum delta over 2. Warranted. Okay? So as you can see, delta is very important. If delta is small, you make a small error. Delta is large, you make a huge error. Very intuitive, right? So next, there are several types of quantizer. So this is a quantizer we call mid-rise. Mid-rise means it rises up right at 0. Okay? There are many ways that you can partition the intervals, right? So this is one way of partitioning the intervals. This is another way of partitioning the intervals, okay? Where this guy, one of the reconstruction points is exactly at 0. Okay? It turns out that this is very popular in compression, and this is very popular in analog to digital conversions. Okay? In compression, 0 is very important to us. We see from the entropy coding design example that the more 0 we have, the happier we will be. Okay? So that's why we're going to concentrate around 0. We try to generate as many 0 as possible. Okay? That's one of the goals. So let me bypass this and let's start with some quantization error analysis. So the assumption is this, okay? I have an x coming in, just scalar, okay? One single guy, okay? It's a random variable with certain PDF, okay? Maybe Gaussian distributed, Laplacian distributed, or uniform distributed, okay? That is one single random variable coming in. It will come in the Q, it becomes y right here, and then coming through the Q inverse, give me the x hat. Okay? The error is defined as x hat minus x. That's what we are. That's the amount of information that we actually throw away, right? So Q, okay, a reasonable thing. Okay, this is called a high bit rate assumption, meaning that you're not trying to make delta too large. Okay? If you're not trying to make delta too large, Q will turn out to be another random variable, usually 0 mean, and independent of x. Okay? These are the type of assumptions that we need to make in order to carry out the analysis. Otherwise, it will be too complicated to work out anything interesting. Okay? So, turns out that y will be a random variable too, x hat will be another random variable, q is also another random variable, and I can model it this way. Okay? So I can model it, okay? These two blocks, I imagine like adding noise to my original signal. Right? Agree? Because q is equal to x hat minus x. Right? Q is x hat minus x. So x hat is x plus q. Right? And that's how I come up with this very simple model. So you can treat quantizer at high rate, just like you are randomly adding noise to the original signals. Okay? And that's why we were playing with some of the MATLAB exercise yesterday, right? That's exactly what it means. You are the quantization noise will be like that. But we add the noise directly to the image pixels. In real life, it doesn't happen like that. Right? We have a transform, like the wavelet transform, the discrete cosine transform or something. Right? We never add noise, we never quantize anything directly. Right? So this is the model, and let me write the mean square distortion measure is the expectation of x hat minus x squared, okay, which is just the expectation of q squared, okay, and this is a function of x, right? This is the quantization. So expectation of q squared is nothing more. If you assume that q is 0 mean, then it's just the quantization error variance, right? This is just the variance of the noise. Okay. So now let's do this simple analysis. Okay, d of x hat minus x is the expectation of x minus x hat squared, and I can write it like this, right? Because that's the definition of expectation. Okay, so and then now you have multiple quantization levels, right? You have multiple quantization levels, so you can break this large integral into smaller one. So for each of the jumps, right? Okay, each of this integral is for one jump followed by the others, right? And these are quantization boundary. This is the reconstruction within the interval, okay? So on and so forth, okay? Now, so I can write this as a summation, right? So I can write this as a summations over L is the total number of quantization intervals that you have, okay? And I go from 1 to L, and I just do the summation of all the guys, and I have my D, okay? So this is the mean square error, quantization mean square error, that we would like to minimize, correct? Okay? So let's try to play, okay, to demonstrate this, let's play with this very simple example. Okay, this is a bounded input, so my x can never go past negative x max and positive x max. Okay, and I have, in this case, I draw 4 quantization intervals, but it can be more, it can be L. Okay, so the center reconstruction give me x hat of I being the middle of these guys, okay? And the how do I get this? Okay, so I'm plotting Q with respect to x, okay? So let's take a little time to try to understand this. Okay? Are you okay with this? What is Q? Q is x hat minus x. Q is x hat minus x. Okay? So, Q is x hat minus x. Or am I drawing it right? Or x minus x hat? X hat minus x, right? That's true. Okay, so if I happen to be, okay, if x hat match with x perfectly, then I have 0 error. Right here. Okay? If I happen to be right here and I got mapped to the red dot, this is how much error I make. If I'm right here and I get mapped to the red dot, this is how much error I make. And the upper bound here is delta over 2. The lower bound here is negative delta over 2. Correct? So this is, I figure this out from just x hat minus x. Okay? Now, so are we ready to do some manipulation? What is the error in this case? So first of all, the error bound is Q equal to is bounded between negative delta over 2 and delta over 2. That's obvious. Okay? And then at the high bit rate assumption means that instead of working with the distribution of x, I'm going to try to map it into the distribution of Q, okay, and work with this plot instead. Okay, so my assumption is this: at high bit rate, there's no correlation between Q and x. Okay, and everything will be uniformly distributed. Okay, the quantization error will be uniformly distributed. That means Q will live somewhere between here and here, and it will be uniform, so the PDF of Q look like this. Okay? Now, if I make that assumption, so the high bit rate assumption is there, and then let's try to do this real quick. Okay? I don't think it's in the is that in our booklet? Yes. Is the answer in our booklet? The slides in the in the text, does it have? Okay, so we're going to do the x hat of okay, the distortion, mean square distortion is expectation of Q squared. Okay, let's compute this quickly for me. Just a couple lines of math, right? So let's see. Oh, I put the question mark there, right? I put the question mark there. So the integral of q squared, and then fq of q is just 1 over delta, right? The integration of integral of q squared is 1/3, q to the 3rd power, right? And then what? Instead of negative infinity, positive infinity, you do negative delta over 2 to delta over 2, right? Because it's 0 everywhere else, okay? So this is how you set up the problem, okay? Q squared, 1 over delta dq, okay? Going from negative delta over 2 to delta over 2, and you work out the integral, you come up with this magical formula, okay? Delta square over 12. Delta square over 12. So this is the mean square quantization error, okay, with all the assumptions that we made. Okay, this is significant because, as you can see, the error decreased, okay, with this square here when you need linearly decrease delta, right? So just improving delta a little bit, you reduce the error by a whole lot, okay, because this has a square sum, okay? So it's critical to have obviously a small quantization bin. However, with a small quantization bin, we're going to increase the bit rate. So that's a trade-off. Yeah. Now, this is 1/3 of x squared max 2 to the 2b, and then the observation is this. If I increase b, which is how many bits I allow you to use for your quantizations, okay, I increase b by 1 bit, I double the amount of intervals, right? If I allowed you to have 1 more bit for your quantizer, okay, 1 more bit to describe the y, okay, I have twice the amount of step size. Agree? Because I double the number of quantization step size, right? So I reduce delta by a factor of 2. Every 1 bit that you give to your quantizer, you decrease the error by a factor of, reduce delta by a factor of 2.
I have a question.
Yes?
We assume that the distribution of delta is uniform.
Adding 1 more bit increase the signal to noise ratio by 6 dB. So this is the famous 1 bit 6 dB gain, okay, in DSP. Let's do another example of quantizer, okay? Designing a 3-bit uniform quantizer for a signal with range 0 to 128, okay? 3 bits. If you have 3 bits, then you can describe 8 levels. 8 levels. Okay? And you know the range is from 0 to 128. So then, delta will be x max minus x min divided by L, which turns out to be 16. Okay? Now this turns out to be 16, so I'm going to index my y level as 0 to 7. Okay? How did I get this? How did I get these magical numbers? How did I get 8? Why 8?
0 and 8.
Right. That's the first, okay, delta is 16. Okay? So my first interval is from 0 to 16, and the midpoint is 8. Okay? The next interval is 16 to 32, and the midpoint is 24. And that's how I get 24. Okay? The maximum quantization error in this case will be less than absolute value of q is less than or equal to 8. Okay? So this is a very typical setup in practice. Okay? We typically know the range of whatever coming into Q. Okay? We decide how many levels we will need. Okay? And that determines the bit rate, right? Okay? Because output Y will be going to the entropy coder, the arithmetic coder, the Huffman coder. Okay? So obviously a small number of quantization levels here will allow you to have more compression. Okay? Now, several other forms. Very popular form of quantization is rounding, flooring, ceiling operator. And I let you figure out, okay, exactly how you will draw the quantization operation. Okay? So let's skip this and let's do optimal scalar quantization. So this is our problem statement. I have a random variable x with a known EDF, fx of x, okay, which I can observe for a long time and kind of figure out, okay, how x behaves. Okay, the goal is to find xk, which, so what does xk? Xk is the decision boundary, okay, and xk hat is the reconstruction, the red dots, okay. So my job is to figure out all the boundaries, okay, and also all the reconstruction, such that the distortion between x hat and x, the mean square distortion between x hat and x, is minimized. Okay, so this is a pretty well posed problem. Okay, now I'm gonna break this problem into two parts. Okay, so the first part is this: optimal encoder for a given decoder. Optimal encoder for a given decoder. Given decoder means what? You know the red dots. Okay? Somebody implement the decoder. We don't have any choice. We don't have any choice with the decoder. Okay? But we have we can make smart decision at the encoder. Okay? Which means we have to figure out the xk. Find the optimal xk such that the distortion is minimized given a fixed x hat. Okay? Somebody determine the x hat. For example, middle of the interval. We don't have any choice. Okay? So how do we do this? Okay? Which means I have to minimize the x hat, which is the formula that I showed you before. Okay? With respect to x of k. Okay? Now, so any suggestions? How do we attack this problem? What would you do? How do we minimize something? We take the derivative with respect to xk, right? We set it to 0, we find, okay, and then if you want, you can take the second derivative and verify that it's actually a minimum, not the maximum, right? Okay, but we take the derivative with respect to xk, not x hat, xk, okay, and then we set it to equal to 0, okay? So this is non-uniform quantizer under consideration. You can put the xk anywhere you want. They don't have to have the same length, even, okay? So you put any xk, you can put the xk anywhere you want. But the x hat dot, okay, all the red dots are being given to us, okay? And reconstruction can be anywhere, not necessarily the center, okay? Somebody designed this already. So this is the problem, and I'm going to take partial derivative, okay, with respect to the little xk of this guy, okay? Now, what do we need? We need the fundamental theorem of calculus, right? Derivative of, so basically the derivative and the integral kind of cancel themselves out, right? So the fundamental theorem of calculus say that if you have a function fx like this, and you take the derivative with respect to x of fx, which is this interval right here, then you get, so ddx of integral of some constant c with respect to x, okay, f of t dt is equal to fx itself. Okay, so basically you cancel the operation here. Okay, now why do I only pick up these two guys but not the entire? Okay, I have L terms in the summation, right? Okay, why do they all go away except these two? I'm taking derivative with respect to xk. Okay, so the x0 will not come into play, the xl will not come into play. I only pick up xk. Anything with xk I pick up, right? So I pick up one xk, which is the lower guys here, and I pick up another xk terms where it's upper, right? And I have to take this derivative, and if I apply the fundamental theorem of calculus, I will come up with, okay, so take derivative separately, you're going to come up with something like this. Agree? So let's take a little time to let it sink in. Okay? Alright, and our goal is to find xk, right? So set it equal to 0, and I come up with, okay, so set it equal to 0, and I come up with this. Xk is equal to x hat of k minus 1 plus x hat of k divided by 2. What does this mean?
It's a relation to the red point.
Right. It's the midpoint. You should put the optimal xk, okay, is the midpoint between the two red points. Okay, you're given the red points. There's nothing you can do about it. Somebody designed the red points. Okay, that's the way it is. But we have control of the decision interval, and the optimal decision is right in the middle of the two red dots. Okay, so this is called the nearest neighbor rule. Okay, so you take two neighboring reconstruction points, the red dots, and put your decision right in the middle. Okay, so that's the first problem. The second problem is the optimal decoder for a given encoder. Okay, so this is the inverse problem. Somebody already designed all these quantizations interval, and your job is to find the optimal red dots. Okay, your job is to find the optimal red dots so that the mean square error between x and x has is minimized. Okay, so this is a slightly different problem. Okay, you're given all these xk plus 1 xk here, and you have to take derivative with respect to the x hat of k. Correct? You have to take derivative with respect to the x hat of k. Okay, so this is slightly easier, right? It's slightly easier because when I take the derivative of this guy, so substitute everything in, I only pick up one term. I only pick up one term, right? The terms where I have the x hat k, okay? K minus 1 and k plus 1, they never come into the equation, right? So I only pick up one term, and then I assume that everything is continuous. I can switch the order between integral and derivative. Then I come up with something like this, okay? Set it equal to 0 means that so you have you break this into two integral, right? Break this into two integral. One guy is like this, the other guy is like that, and your job is to find the x hat of k. Okay, so the solution turns out to be something like this. Now let's step back and take a look, see if it makes sense. What exactly is it trying to say here? The optimal reconstruction point, which is the red dot, should be where? Now let's take a look at the denominator, okay? So this is simply the integral of the PDF of x. So this gives us some number, right? It's just a scaling number. It's not that important, right? So this is a scaling number. This is just a scaling scalar. Okay. What about the guys up here? That's the expectation. That's the expectation of x. Okay, the expectation of x within the interval. Within the interval. With fx of x. So if it's uniform, guess where the expectation comes in? In the midpoint. Okay, fine. There's no problem. But if it's Gaussian, suppose I have a Gaussian like this, and this is the interval xk minus 1 and xk. Okay? The midpoint is here. Okay? That's not optimal. The optimal thing to do is the expectation, which will move this guy over a little bit. Okay? That's exactly what it's trying to say. Somebody already give you this xk minus 1 and xk. You cannot control it. Okay? But you can control the reconstruction. Okay? And in this case, what you should do is to move the reconstruction over to bias this region where it's more likely that x falls into play. Okay? And this will minimize the mean square error. Okay? So these are the two. So this is called the centroid rule. The centroid rule, which says that the optimal reconstruction point is the centroid of fx of x in this particular interval. If you move on to this interval, maybe it will happen to be in the middle. Okay? So it all depends. So those are the two fundamental theorems that we can say about quantizations. Now, but we run into a little problem, right? We're cheating. We're breaking up the problem into two parts, and then, okay, we solve the optimal encoder given the decoder, solve the optimal decoder given encoder, but we don't have any solution for the joint problem, right? Right? If you, the entire point is the point between x and x hat. Whatever happens in the middle, you don't really care. Okay? So that problem is being solved by Lloyd and Max all the way in the 1950s. Okay? Unfortunately, we need x hat k to solve for xk, and then we need xk to solve for x hat k. Okay? So it's a chicken and egg problem, right? Okay? And well, when you encounter a chicken and egg problem, the only thing you can do is think of something iterative, some kind of iterative algorithm. Okay? And so this is the idea is first being published by Lloyd in 1957, and then Max independently discovered the idea again in 1960, and they typically call the Lloyd-Max quantizer. So you're going to solve these two equations iteratively until D converge, or D doesn't decrease by a whole lot anymore. So this is an ad hoc engineering technique that allow us to run around the problem, because we just don't know what else that we can do. Okay? So basically, this is what happens. You have the nearest neighbor rule, and you have the centroid computation rule. Okay? And so you're gonna start here. You apply the nearest neighbor partitioning. Okay? And then you use the centroid computation on it, and then you update the code book. You feed this code book back here and try to do this again. And everywhere you go, you compute the distortion. Okay? And you let it run until D doesn't seem to decrease anymore. So in one of the homework assignments that we passed out today, we're going to have a simple exercise. You don't need to iterate. You only need to iterate maybe once. Okay? You're given a nice Laplacian. And then I ask you to design the optimal quantizer. And it turns out that with that problem set up, you don't you basically get the result doing this only once. Okay? So there are cases that you don't have to iterate anything. Yeah? But in practice, typically, we need to set up this problem. Okay? Now, the assumption is the PDF is known and stationary, and this is very important. Entropy has not been taken into account. Okay? So all the optimal things that we have been discussing about, okay, is just quantization by itself. Quantization by itself. We never take into account that we have entropy coder following up on our quantization solution. Okay? So that turns out to be a major problem. Okay? Because remember the goals for entropy coding is to generate as many similar symbols as possible. And in this case, hopefully 0, right? We like 0 a lot in compression, by the way. Okay, 0 means small, 0 means insignificant, 0 means you can throw them away. Okay? We only keep the large guys. We always throw away the small guys. So we like 0 a lot. Okay? The goal of doing quantizer is to generate as many 0 as possible. Okay? To generate as many 0 as possible, so that your entropy coder will do a very good job. Okay? So then, But I would like to discuss another type of quantization, which is actually being used in practice a lot. And this time, we actually take into account that we want to carry a lot of zeros. Okay? So how do we do this? So this is the random variable x, and I assume that maybe it's living on the real line. Okay? Living on the real line means you need infinite amount of bits to represent x. Okay? So that infinite amount of bits come in the integer form, decimal space, and all these binaries that describe the decimal part, the fractional part of it, right? Okay. So 1/2 means you have a 1 here. Okay. 1/4 means you have a 0 here and you have a 1 there, so on and so forth. Okay. The way that we represent binary using for fractions. Okay. So x is going to be a combination of integer part and fractional part in binary. So these are binary with assignments in the beginning. Okay. So x is here, y is here, and x is there. Okay. And this is what embedded quantization does. I'm going to discard n integer bit planes. N integer bit planes meaning I discard n guys here and all the fractional bits. I'm going to throw away all the fractional bits. Okay? And further, I'm going to throw away several integer bits. The least significant bits. Okay? And I call this y. So this is going to be y. This is a very easy thing to do, right? This quantizer is very easy to implement. You don't need to do anything. In fact, x coming in, you throw away the guys in the back, and you only keep the most significant bits, a few most significant bits plus the sign bit. That's it. Okay, it's very easy to do in practice. It's absolutely wonderful. Okay, and it turns out that JPEG 2000 is using this embedded quantization technique. Okay, so let's investigate this and see how y behaves. Okay, how x hat behaves, so on and so forth. Agree? So let's see how y behaves. Okay, and you can think of this as the most significant information is being transmitted first, right? So first we're going to transmit the sign bit, then we're going to transmit the most significant bit, then we're going to transmit the next most significant bit, and we move on until we run out of bit rate. Okay? Which is a very, very easy thing to do in practice. Okay, so let's think about our mapping. Okay? What exactly is the mapping between x and y and the x hat? Okay? So x is the input of the quantizer, y is the output of the quantizer, okay, in the middle. And then the x hat will be somewhere in the middle here, right? Which is the reconstruction. So let's take this very simple example, okay? I will have bounded input, x between -16 and 16. So this is -16 and this is 16. Okay? I will throw away the two least significant bits. I will throw away the two least significant bits. Okay? So, how do I work out this problem? I will throw away the two least significant bits. So I have this. Okay, the decimal points is right here. So I throw away all the fractional parts. I also throw away the two least significant bits. Okay, but I keep the rest. And this is y with a sign bit right here. Okay, now let's think about this. Okay, how many bits do we need to represent anything from -16 to 16?
5.
5 or 4?
5. Include assignment.
Okay. You need to take, okay, all you have to do is 15.999999999, okay? Okay? How do you get 15.9999999?
15.
So I need 1111, which is 15, right? And then, guess what? I need a lot of 1 here, right? That's how I get 9999999. Okay? So I'm gonna throw away all the 1 here. Okay? Oh, well, I need a sign bit here as well. Okay, so you're right. I need 5 bits. 1, 2, 3, 4, 5. Okay, I need the sign bit plus the 4. Okay, and then I'm gonna throw away these 2 guys as well. Okay, so I only keep 3 bits. The sign bit plus the 2 guys. Okay, now let's think about, so where is it right here? What is the first? How do I get 0 out? How do I get 0 out? I need the sign bit to be 0, right? And I also need 0, 0, right? Okay? So what is the maximum number that I can represent if it's 0, 0, 0 here?
3,
1, 1, 1, 1, 1, 1, like this, right? So what is this? 3.999, which is roughly 4, right? So this is 4, and this is negative 4. Agree? So that's 4 and negative 4. Not including 4, okay? Excluding 4, excluding negative 4, but that's how I get 0 out. That's how I get 0 out, okay? How do I get 1 out? It would generate a lot of 0 for us, right? It would generate a lot of 0 for us. And that's why this is very effective in compression. It generates a lot of 0 for us. Okay, so this is called a double dead zone. Dead zone means you fall into the dead zone, you get 0. You get eliminated. Okay, you will never survive. Okay, so this is a double dead zone quantizer, and so this is fine. How do I put the reconstruction point? How do I put the reconstruction point? Well, in the middle is one way, right? But the optimal way is what? We observe the PDF of x, right? And put the midpoints accordingly. Okay? So that's the optimal thing to do. Now, if you choose the midpoint reconstruction, which is usually a pretty reasonable thing to do at high bit rate, okay? Then the midpoint will turn out to be the red dots or the reconstruction. Okay. Now, if I have the red dots, I'm going to show you if let's say I want the midpoint as my reconstruction. I'm going to show you very quickly how we can inverse quantize this in a very smart way. Okay? So let's take this original symbols. Suppose that x coming into the quantizer has value 22. Okay? So 22 is 1, which is the sign bit. Okay, I don't have a sign bit now. Okay, so I just ignore the sign bit. Okay, so let's ignore the sign bit. So this 22 is 1, 0, 1, 1, 0. Okay? Alright? Now, if I throw away the 4 bit length, okay? If I throw away the 4 bit length, then I only keep 1 plus the sign bits up here, okay? Then, so in the decoder, you receive 1 bit at a time, right? You receive 1 bit at a time, and the first bit you receive is 1. You haven't received these, okay? You receive the first 1 bit. Can you reconstruct? What do you mean no? What is, okay, suppose that I receive 1 and then my communication line gets cut off. I have to reconstruct now. What am I going to do? Can I think, what is the range? Okay, if I'm a smart decoder, right? I receive a 1. Is there anything that I can say about the behavior of X? It lives from where? 16 to 32. Right? Is that a good guess? It's not a guess, it's true, right? I receive a 1. Okay? So I know the range is anywhere from 16 to 32. I don't know exactly where, but I can tell you that's the range. Okay? I can tell you that's the range. So if I have to reconstruct now, what would I do? The midpoint, right? Okay? Suppose that I don't know anything about X, okay? I'm blind, Okay, and I'm trying to make reasonable guess. I'm going to guess the reconstruction is in the midpoint of 1632, which will give out, turns out to be 24. Agree? Now, let's take it one step forward, okay? After we receive that one bit, our communication channel opens, and then it leaks us another bit. Gives us one more bit, okay? So it gives us one more bit, 0. Okay? What can I say? And this is called the refinement bit. Refinement means you update. Okay? So I receive another 0. What is my range now?
16
It's still 1632, correct? Okay? But then since I receive a 0, I'm going to be able to guess that it's in the lower half. It's in the lower half of 16 and 32. Right? It will be in the lower half. It cannot be in the upper half. If it's in the upper half, I should receive a 1. Correct? Okay? So I'm going to be able to guess that my range is now 16 to 24. And if I suggest the midpoint reconstruction, that's going to be 20. That's going to be 20. Okay? Now, this is interesting. Take a look at 20. 20 is 24 minus 4. 20 is 24 minus 4. Minus because I receive a 0. If I receive a 1, what is it going to be? Plus 4. So it becomes 28. And again, that's the midpoint of the upper range. Okay? So see, this is called a refinement quantization. Because the more bits you receive, okay, the more refinement that you're going to be able to do. And guess what? We're coming closer and closer to 22. Eventually, we're going to hit 22. Okay? So the next step is I receive another 1. I receive another 1. Which will, so I'm going to be able to say that this range will be the upper part of 16 to 24, which will put me at 20 to 24. Put me at 20 to 24. The midpoint is 22. The midpoint is 22. And I get 22 by taking this 20 right here. I add 2 to it. Okay? Add 4 or add 2 depends on where you are. Okay? Add 2, add 4, add 1, add 8, minus 8. It depends on where you are on the bit plane. Okay? So you must know where you are. So I'm making an assumption that I know where I am right here. Okay? So the encoder has to tell the decoder that this first bit lives on the 5th bit plane or something. And that's how you can do this entire process. So this is called embedded quantization and embedded inverse quantization. The way that you do quantization is simply sending 1 bit at a time. You take this and you send 1 bit at a time. First you start with a sign, and after that you send the most significant bit, the next most significant bit. You keep on going until you run out of bit rate. Okay? At the decoder, this is what happens. Okay? Okay, so you can wait until this guys get here, or you can do reconstruction 1 step at a time, like this. Okay? So in this case, we get lucky, right? I don't need the last 2 bits and I already get 22. But I get lucky. I don't always get lucky. Okay, sometimes we get lucky. Okay? And that is you can show that this bit plane truncation idea or embedded quantization is actually just a scalar quantization with step size delta being equal to 2 to the n. And then the middle step size is twice this large. Okay? This is being used in JPEG 2000. We will revisit this guy in the second part of a lecture in a few minutes. Okay? Before we take a break, I'm going to just spend 1 minute talking about something we call vector quantization. Okay? So what we have been talking about so far is called scalar quantization, meaning that 1 guy coming in, 1 guy coming out. Okay? Vector quantization is an n-dimensional generalization of scalar quantization. So instead of 1 guy coming in, you have 2 guys coming in, two guys coming out, so on and so forth. So you are doing grouping, okay? So if you do 1, 1 like this, then if you have two guys, x1, x2, follow, concatenate two guys, one after the other, so we can call this separable scalar quantizer. That means we put all the midpoints right at the nice grid, okay? But if I have a two-dimensional signal, and I want to do two guys in, two guys out, then you will be able to do something like this, okay? Which definitely should be a lot more effective in terms of the trade-off between bit rate and reconstruction errors. Okay? Because over here you are forced to use square. You cannot use anything else except square. But over here you can come up with other geometrical shapes. Okay? Now, vector quantization is supposed to be an improvement over scalar quantization. However, with entropy coding following up quantizations, then it doesn't turn out to give you a huge advantage anymore. Okay, it turns out that the advantage is pretty small. So that's why in practice, all you see is scalar quantizer. You rarely see vector quantizer except in the academic environment, where people are actually interested in mathematical result rather than practical implementations. It should be a lot more difficult to implement these beehive shapes comparing to this very straightforward square, right? So, so far, let's do a quick summary. So far, we motivate the we introduce the motivations to image and video signals, compression, communication, processing. Okay, and we cover two major parts of our framework, of our compression framework: the quantization part and the variable length part. Okay, let's take a break, and when we go back, we're going to start thinking about the T-box and how to design the transform that can be used together with the quantizer and the entropy coder to connect them together into a nice complete codec. Okay, so see you back here in about 10 minutes. Now, so let's see. We cover quantization, we cover entropy coding, so we cover 2 out of 3 in our original transform coding framework. Okay? So the last step to complete the entire framework is the transform part, or the prediction part. Okay? And we're going to try to do these things today. So we would be lucky if we cover up until this point. Okay? From now until 12. So we'll first start with simple prediction. Okay? Prediction is still, say, I'm at location K, okay? And I have my neighbor at location K minus 1, K plus 1, K minus 2, K plus 2. How do I predict myself from the observed neighborhood? Okay? That's the first thing that people try when they try to decorrelate something. So that's the prediction technique. Then after prediction, people get a little smarter. And people say, instead of predicting one guy at a time like that, okay, which can be pretty inefficient, okay, we're going to try to predict an entire vector together, or an entire block together. And that's where the transform comes in, right? We talk about, I'm going to talk about vector space and how to do linear predictions, okay, of a vector space using the fewest amount of coefficients, right? So it depends on the basis functions, right? So you design a good basis functions which will allow you to approximate whatever signals using a very few number of coefficients. And instead of sending the pixels or the samples or whatever over, we send the coefficients over. We send the coefficients over, right? At the other end, at the decoder, the decoder will use all the, it knows the basis function that the encoder use those linear combination, reconstruct. And that's where you have the state-of-the-art transformation techniques, okay? And then the next question to ask is, how do we design the basis function? Okay, so that's the main part of today's lecture. I'm going to try to show you the optimal linear transform and hopefully convince you that under certain assumptions, we have the discrete cosine transform which come pretty close to the optimal linear transform, the KLT here. And then we also have techniques like the weighted transform, which is the new kid on the block, right? New guys coming up the rank that can do also very, very well. So, and in our MATLAB demos and exercise, we're going to try to compare different transforms, right? And hopefully convince you that some will perform better than others. Okay? So obviously, wavelets perform slightly better than the discrete cosine transform when it comes to only images, still images. But when it comes to video, this guy is still holding the lead. Okay? And obviously, I have to defer that until tomorrow when we talk about video only. So the reminder is we cover E, we cover Q. Okay, we kind of know the behavior of these guys pretty well. Okay, so the remaining job is to define T and the appropriate T inverse so that we will complete the framework. Okay, and typically people will do either prediction here or transformation here. Okay, some kind of decorrelation engine. Okay, take away the correlation between the sample of the input signals. So, so far we have only dealt with memoryless models. That means we never cared about the neighbors. We try to do a little bit with run length coding, but other than that, we're processing one guy at a time, one sample at a time, one coefficient at a time. Okay. There is usually very strong correlation between neighboring symbols, and we can easily confirm in MATLAB, right? We can just randomly go into any natural image you want, pull out an 8x8 or 4x4 plot, and see the behavior of the coefficient, and you can see that most of the time they're very close to each other. Okay, meaning that there are a lot of correlation, and we can so like Edmund showed yesterday, the random image doesn't have any structures, right? It doesn't seem to have any interesting behavior, but the natural image seems to have a lot of correlations, a lot of edges going together, a lot of smooth regions, right? These are the things that we can take advantage of to do very good compressions, okay? So the simplest prediction scheme that we can do is to take the difference, okay? Right? You just take the difference between you and the neighbors, and just instead of encoding each samples, we encode the difference, okay? That will reduce the entropy a little bit, okay? But we can do a lot smarter things, okay? So the most primitive prediction techniques is called DPCM, or differential pulse code modulation. Okay, just a fancy name for this operation. Okay, this operation is this. I take my input signal X, okay, and I subtract my neighboring samples, which is xn minus 1. I have the difference, okay, and instead of doing x and x minus 1, I just feed D into Q, and then that's my encode. Okay, so instead of encoding x, I encode the difference between x and the neighbors. Okay, feed it into Q, feed it through the entropy coder here, go through the communication check. Okay, how do we reconstruct?
We use dn and is and minus 1.
Yes, right. We add D back to x and minus 1. We construct x. Okay, so the reconstruction looks like this. So this is the inverse quantizer. You have the D hat. Okay. Now, and then you add it back with the x hat n minus 1, and you get back the x hat. Now, if you throw the quantizer away, if you make dn equal to d hat n equal to dn right here, you can easily show that you get perfect reconstruction. Okay, you get exactly yourself back. Okay, Now, so the quantizer determines the trade-off between bit rates and reconstruction quality right now, right? Now, so yeah, let's do this analysis, okay? Again, D hat is D plus Q. That's our quantizer model, okay? And so D hat is there, okay? So I have D hat equal to D plus Q. And then in the encoder, I have D equal to xn minus 1. So at the decoder, I have x hat equal to D hat plus x hat, okay? So let's start with 0, okay? D hat of 0 is just D0 plus Q0. So I reconstruct x hat of 0 like this, okay? Now, x0 is the starting point. There's no neighbor, right? Or there's no previous observation. So you just do it by itself. Okay, there's no difference, right? You just quantize x hat x directly. So x hat is just x0 plus q0, which is the error you make, okay? But now the problem comes when we do the next step, okay? So the d hat in the next step, okay? And this is the reconstruction. So x hat 1 is equal to d hat 1 plus x hat of x0 based on these formulas. And substitute everything in, okay? I have something like this. Okay? Now, what is the problem? The problem, I manipulate the, okay, so basically just using these equations, I manipulate it to get it into this form, and I'm going to see that xs1 is equal to x1 minus x0. Okay, it looks like our original prediction scheme, and then all this. Okay? So, you will be able to show that x hat is equal to, x hat 1 is equal to x1 plus q0 plus q1. Plus q0 plus q1. Okay? That's a significant step. Because if you do this n times, okay, it will be pretty easy to show that x hat n will be equal to xn, which is the original signal, plus a bunch of quantization noise. This is bad. Right? This is called accumulation. This is called quantization error accumulation. Because the error between x hat and x turns out to be a summation of those q. Okay? And, well, you can always try to bank on the fact that they have zero mean. If you do a bunch of them, they cancel themselves out. But there's no warranty, right? Sometimes it can be really bad, right? So typically we would like to avoid a situation like this. Okay? How do we avoid problems like this? We recognize that there is a mismatch between the encoder and the decoder. Okay? In the encoder, we do this. Okay? But in the decoder, we do this. Okay? So, looks like there's a lot of difference. Okay? We have a difference here, and we also have a difference here. There are two differences. That's why there's an accumulation. Okay? So, let's try to fix that. How about using the reconstructed sample for the difference? That way we reduce the mismatch, okay? And I will propose this. Instead of using this, I propose using that, okay? So instead of predicting x, okay, predicting from the original samples, I predict from the reconstructed sample, okay? And that turns out to be a better scheme. So the modified scheme looks like this. Dn is equal to, which is the difference, is xn minus x hat of n minus 1. Meaning that this comes from the reconstruction. This comes from the reconstruction. And it's trivial for you to show that, so the decoder remains the same, okay? We don't change the decoder, but we change the encoder. We change the encoder, and we'll be able to show that, so when you go home tonight, you can just take a little piece of paper with a pencil, okay, work out the details, and you're going to be able to show that x hat n is equal to xn plus qn only. So there's no more summation of the q, okay, if we use this scheme. So this is called a closed loop, BPCM. This is the type of prediction that people in video coding use all the time, okay? So the difficulty of this scheme is that you need the reconstruction. You need the reconstruction at the encoder. You need the reconstruction at the encoder. What does that mean? That means the encoder knows everything. The encoder has the decoder, right? That's how it decodes this X hat, and then use that reconstruction for future prediction. Okay, so that makes your encoder a lot more complex than before. Okay, because encoder has to be twice now, right? So it makes this scheme looks a lot more complicated. Okay, so this is the updated encoder. The encoder will have everything. It has the encoder, the original encoder, and it also has the decoder built in. Okay, so that we can reconstruction along the line. So you can show that by following the signal flow graph, you can show that the dn right here is xn minus x hat of n minus 1. This D stands for delay. Okay, that's anything passed through D will have an n minus 1 index. Okay, so because we're kind of running out of time, let me move through this a little. Yeah.
Here we assume that communication channel is perfect.
Yes, exactly. Exactly, right. If it's not perfect, there are a whole lot of things that's going to be good. Yes, right. This communication channel is an entirely different topic. Okay, right now, let's not worry about that. Let's assume that we're going to have a decent communication channel, and in practice, we do have decent communication channels, right? When I write you an email, it arrives exactly the same. Okay, it's not going to get any error. Okay, so we do know how to build very good communication channels. Okay, at a cost, of course. Yeah, that's another issue. So for now, let's just assume that we have a very good communication channel. We'll revisit this when we have time. Okay. From Zoe. So the generalization would. So this is how actually research is being done. Suppose that somebody proposed DPCM and you read it, and the first thing that you should always ask yourself is that, okay, can we make it better? Can we channelize that to something a little bit more intelligent and get better performance? So generalization of the scheme. Okay. So one thing that we can do is to replace a simple delay operator. So instead of predicting xn from just x hat of n minus 1, okay? Maybe we will predict from more than just one guy, or a linear combination of the past samples, right? So we will be able to use something we call a predictor, or just a filter operation, just any filtering operations, right? And hopefully we're going to do better than a simple delay, right? The delay in N-Jones course is just a very is a trivial filter, right? Delta of n is a very boring filter. It doesn't really give you much, a very good performance. So usually you do a lot better so we will do this upgrade, right? We upgrade this delay operator by some kind of prediction operators, okay? So this P typically is an FIR filter, okay? And as you can see, if I put P here and P here, everything works exactly the same way, okay? It's still a closed loop design, okay? It behaves exactly the same way, but it just may be offering you a better prediction, so that dn will be smaller. Okay? The entire goal is to make the prediction small, okay? So that we can compress it better. So xn, pn, you can think of pn as an operation that give you predict x hat of n based on the observation, based on these observations. These are the past observations. Okay, you already see them. You know some kind of behavior, and you use the past samples to predict the current one. Okay, so you can write it as a linear combinations, and this is going to be what you're using to predict xn. Okay? So now, next question. How do we find out this AI, right? Which is the weighting cost. That's the main thing. Right? Basically, how do we design the filters here? So that, what? So that the PS, the mean square error between x and x hat is minimized, for example. Okay, that is a very common thing to do. Okay, so let's try to pose this problem. This is called the optimal linear prediction problem. Okay, and I don't know if anyone covers that, but it's a kind of this. We're going to show that this is just a winner. Okay, we can, if we observe the autocorrelation, the correlation between the samples, we'll be able to design these filters in a few mathematical steps. Okay, so I'm going to pose this problem. Find the set of AI, such that the distortion or the variance of the noise, okay, between xn, which is the current samples, and the prediction is minimum. Okay? Now, if this is minimum, dn will turn out to be very small. Will be the smallest that you can ever produce. And that small guy, when you go into Q, will generate a lot of zero, and those zero coming into the entropy coder will give you a minimum amount of bits that you can send over the communication. Okay? So that's the key. Okay? So how do we do this? What's our dear friend? Our dear friend is the differentiation operators, right? Let's take derivative, set it equal to 0, right? That's what we do essentially, most of the time. Okay? So how do we take derivative of this guy? Yeah, just do partial derivative with respect to AI, right? Okay? But before we do that, I think I need a couple of assumptions. Okay? The assumption is that my signal will be Y-stand stationary, because I don't know how to deal with multi-dimensional signal very well. Okay? Too bad. Y-stand stationary is pretty much the only random process that allows us to do simple mathematical derivations. Okay? I'm going to assume we have high bit rate, so fine quantization, so that I have that uniform distribution in the noise. Okay? It's also another very typical thing to do. And let me remind you that Y-stand stationary means that the expectation of xn with xn plus k is only dependent on k, how far you are away. That's it. Okay? Which is pretty reasonable in a lot of natural images. The farther you are away, the less correlation you have. Okay? So, and Pn, so Pn typically look like this, okay? Pn in closed loop is has the hat, okay? But I'm going to make this assumption as well, okay? That with high bit rate, okay, having hat or not having hat is roughly the same, okay? Because you have very small quantization step size, so you make very little error, okay? So I'm going to make this approximation, okay? So this is actually the optimal linear prediction in terms, this is an open loop design, right? Open loop. Closed loop means you have the hat. Open loop means you don't have the hat, okay? So this is open loop, and the approach is taking the derivatives that are equal to 0 and all that, okay? So let's think about this. How do I do this? I take derivative of d with respect to ai, and the only terms that, so I have to do this for a0 and a1 and a2 and a3 and a4, okay? When I do a0, I pick up only one guy, right? The first term. No, sorry. I do a1, a2, a3, the way I write my summation, okay? So first I'm going to do a1. First I'm going to do a1, right? When I do a1, okay, remember I have the square here. I switch the orders of expectations, which is an integral with derivative, okay? And take the derivative of the guys inside. I have this 2 here. I have the negative sign because I have a negative sign here. And then the chain rule give me x of n minus 1. Okay? I only pick up the first guy, right? So if I do it with a2, the only difference is the chain rules allow me to pick up n minus 2 instead. Okay? So on and so on. Right? So right now I'm still staying closed loop, right? I still have the head. Okay? Now, and I keep on doing that until the end, the last guy, and I have this set of equation. This set of equation, when I try to write it, okay, so the expectation of x, okay, so let's take a look at one equation. Okay, take a look at the first equation. This equation, when you set it equal to 0, you distribute the expectation in, you will have two parts. The first part is the expectation of xn times xn minus 1. The second part is the expectations of xn minus 1 multiplied by that ugly prediction. Okay? So there are two parts, okay? And if you separate the two parts, you have something like this. So for the first equation, I pick up expectation of xn times xn minus 1 equal to that. Okay? And for the second equation, I have this. For the third equation, I have so on and so forth, all the way to the end. Okay. Now this looks kind of messy. But we can always write it as a matrix multiplication. Okay? So how do we do this? So this is a linear combination, which is perfect for writing things as a matrix, right? So I'm going to have this terms and multiply by a whole bunch of a's, right? So I have a1, a2, a3, that's a vectors, and that's going to be equal to this vectors. Okay? So I'm going to try to write it as a matrix. Okay? And before I do that, you should recognize that the expectation of xn and xn minus 1 is nothing more than rxx of 1. Okay? So you can do all that, get to here, and then if you write it in matrix form, it will look something like this. Okay? It will look something like this. Now, what can we say about this matrix? What is this? It's a symmetric matrix. It's called the autocorrelation matrix. Okay, that I show you in one of the slides I had in the beginning. So this is the autocorrelation matrix. This is the correlation between you and yourself. This is the correlation between you and your next door neighbors. This is whatever with a 2 means the correlation between you and your second door down neighbor. Okay? That's all there is to it. And over here you also have the same thing. This is the correlation between you and your next door neighbor. This is the correlation between you and your second door down next door neighbor, so on and so forth. And if I write it, so this is the correlation matrix for the Y-sense stationary process. And this is called the cross correlation vector. Okay? And we can write it in a very simple matrix form, which is Rx times the vector A is equal to the vector P. Okay? And the optimal A will be given as Rx inverse times P. So this is the classic Wiener solution, okay? Discrete Wiener solution for linear prediction. Okay? Now, in practice, how do we actually use this? How do we come up with this Rxx matrix and and cross correlation vectors? We do time domain approximation. Okay, we observe a lot of data, and you approximate it from time averaging of the signal. So after you observe a lot of data, you keep on doing the summations of all the correlation. Okay, sum them up, and hopefully it converts to something else. Okay, but that's roughly all that we know how to do. Okay, so this is called the optimal linear predictions. People actually use this in a lot of adaptive filtering problems, and people also even use this to predict the stock market and everything without much success. Okay. So now that we know how to predict one single sample. Okay, let's try to generalize and try to predict a vector of symbols together. Okay, and in that case, we need some the framework called linear signal representations, which I'm going to talk a lot about. Okay, so here we have an input vector x. Okay, being represented as a linear combination of the phi, or the basis function. Okay? Now, these yi is called the coefficient of the linear representation, and they are obtained by taking the inner product between the input and each of the basis functions. Okay? So basically, it's just a vector multiplication like this. Now, the approximation is this. Okay? Doing the summations over 0 to n minus 1 of everything, and suppose that you don't quantize the y. If you don't quantize the y, you get back exactly the same x as you feed it. Okay? Because when you design a basis function, you will think about perfect reconstruction, invertibility, and everything. Okay? So let's take a look at this. This is the input signal. This is the transform coefficient. This is the basis function. Typically, in a compression framework, these are the guys that will be quantized, entropy coded, transmitted over the communication channel, and get reconstructed like right here. Okay? We never send the pure sample. We send the coefficient. Okay? And the goal is maybe trying to use as few coefficient as possible. That's one goal. The second would be trying to use for the one that we keep. Okay, we should use the minimum amount of bits to describe those y that we actually kept. Okay, so those are the two goals for compression. So if you take a look at this problem from a matrix viewpoint, matrix vector viewpoint, it's actually pretty simple. You have x coming through an analysis transform, giving you y, coming through a quantizer, and in this case I'm lazy, so I write the Q and I combine my Q and my Q inverse together into one box. Okay, and I also have maybe my communication channel right in the middle here as well. Okay, and then so this is my encoder. At the decoder, I have, after the communication channel, after the inverse quantizations, I come up with the y hat. I pass it through the synthesis basis functions, and I come out with the x hat, which hopefully is a very close approximation of this x. Okay? So in the 1D analysis transform, we have something like this. Okay? This is my x coming in. This is my vector y coming out. And I get all these y by doing the inner product. One basis function multiplied by this, second basis function multiplied by that, last basis function multiplied by that. Okay? So at the so that's the analysis. At the synthesis, okay, you get x by a linear combination of the basis function. So you can write it this way. These are my basis function. First basis function, second basis function, so on and so forth. Okay? Now, I have the hat here to indicate the case where I might have a different basis function on the analysis side and the synthesis side. This is called the bi-orthogonal case, right? In the nicest type of transform, we have orthogonality. And what that means is the transpose, TA transpose give you TS. In that case, you just have phi here, phi0 here, phi1 here, without the hat. But that's a subset, okay? That is the nicest case. But it doesn't mean that you there exist other basis functions that have different analysis and synthesis sides. Okay, there's nothing wrong with that. In fact, in practice, like the Weber transform that we use in practice actually has the hat here. Okay, but the DCT doesn't have the hat. The discrete cosine transform is truly orthogonal, doesn't have the hat. Okay, so there are two things. First, you need invertibility, at least, okay? Because that allows us to get back the original signal, okay? If we have TS equal to TA inverse, we're fine, okay? So we know that all the error come from Q and the communication channel, not the transform, okay? So that's what we want to do. So what that means is you need this condition. The dot product between phi I and phi hat of j is delta I minus k, and that's just a fancier way of writing this invertibility equation. Okay, For unitary or orthonormal transform, okay, then the transpose is the inverse. In that case, you don't have the hat anymore. All you have to do is Phi dot product with Pj give you delta I minus j. So this Fourier transform has this property. Discrete cosine transform has this property. Discrete sine transform has this property. Some of the wave construction that we talk about in the Jones course has this construction, right? For example, Haar wave has this property. So now, one of the most fundamental observations that we have in compression with respect to transform is called norm preservation. Okay, the norm preservation property of an orthonormal transform is the properties. I think I put a question mark on your slide. Okay, but what I want to show is that the norm of y minus y hat is the same as x minus x hat. That's the norm of x minus x hat. Okay? I want to show the norm of y minus y hat is the same as x minus x hat. Okay? So let me substitute y by tx, okay? And y hat is tx hat. Okay? Factor out t, so I have this, right? And how do I get norm? Let's do inner product, right? So when I do the inner product between these two guys together, I have the inner product of t x minus x hat and t times x minus x hat with the square root. That's the definition of norm, right? Norm, L2 norm, okay? So that is equal to the dot product here can be written like this, okay? And guess what? What is this? TA transpose times T. That's identity. So they disappear. Okay? What is left? So what is that? What is left? That's the norm, the L2 norm of x minus x hat. That's the L2 norm of x minus x hat. Okay? Now, so why is this important? Any idea? Why is this important? What is x minus x hat? That's the error in what domain? In the time domain, in the space domain, in the original signal domain. Okay? What is y minus y hat? That's the error in what domain? In the transform domain. Okay? And what we just showed is that the error in the transform domain is exactly the same as the error in the time domain. Okay? So our goal is typically trying to minimize this, right? So what we should do is we should minimize the error in the transform domain. So we should treat all the transform coefficients that we feed through the Q and the quantum entropy coder exactly the same way, right? We would like to minimize the loss on the transform coefficient. And it also give you another idea, okay? In the transform domain, okay, if you throw away the small one, if you throw away the small transform coefficient, is the error large or small? Should you throw away the small guys or the large guys? In the transform domain, should I throw away the large coefficient or the small coefficient? The small coefficient, right? Because we make the least error when we throw away the small guys. So that's the key, right? How do we keep the large guys, throw away the small guys? Or when I make error, I should make small errors. I should make large errors in the transform domain. Okay? And that's why we love zero so much. Okay? Because if I have zero, I don't make any error. Right? If I have zero coefficients, I don't make any error. Is that true? Right? If I have zero coefficients, then I don't make any error. That's very important. And that's what we are trying to do when we, in other words, when we design transform, we have to take into account, okay, we have to design a transform such that it will be able to capture most of the energy using a few coefficients only. And the rest should be zero or close to zero. That is the way to go. Okay? So we should concentrate on the quantization of the transform coefficients. And next, let's talk about 2D. Okay? Because so far, with this, okay, with all this, we can only do 1D. We can only do transform in 1 dimension, right? So how do we do transform in 2 dimension? Any suggestion? How do we do transform in 2 dimension? We should do all the rows and then all the columns. Okay? Or all the columns and then all the rows. Because the order doesn't really matter that much. Okay? So in 2D, this is what happens. Okay? X is n by n, and y is also n by n. So this is an n by n block of input signals. So for example, 8 by 8. Okay? Y is another 8 by 8 block of transform coefficients. T is the 8 by 8 transform matrix. Okay? So when you do it this way, what it means is that I'm transforming the columns. I'm transforming all the columns of X. And then I'm transforming all the rows of X. Okay? So if it's 8 by 8, I have to do this 16 times, right? Transform all 8 columns, and then 8 columns, and then transform 8 rows. Okay, separately. Okay? And in the synthesis, if I do this, I'm fine, right? In the synthesis, let's try to verify, right? In the synthesis, I need X is equal to Ts times Y times Ts transpose, okay? And substitute Y in here, I have Ts times Ta times X times Ta transpose times Ts transpose. These are inverse pair, right? Ts is the inverse of Ta, so it's an identity, cancel. This is also the inverse pair transpose. So identity transposes itself, so I get my X back. So everything is all fine, okay? And if I pick Ts and Ta right, all I need is Ts is the inverse of Ta. If I have Ta transpose here, that's even better. That's the orthogonal case. Okay? So that's what happens in 2D. And in 2D orthogonal, you put the transpose here. This is identity. This is another identity. You get your signal back. The nice thing about orthogonal is that you don't have to worry about designing the synthesis. Okay? It's automatically given to you. And it also has this norm preservation property. Okay? If you have Ts instead of Ta transpose here, okay, you cannot have really norm preservation. So when you don't have orthogonality, you have to make sure you're close. You're close to it. Okay? If you're too far away, you lose this norm preservation property. And it can be, then you have to be really careful. So, an example of this would be the DFT that I'm just trying to repeat a lot of the things that Min said before. So, for n equal to 4, it turns out that the matrix looks like this. And you can easily come into MATLAB, type these things in, verify that it's actually, orthonormal. Okay, actually no, it's orthogonal because I'm not scaling the one up here. Okay, now so this is the DFT, and the next question that you should ask is that fine, there's so many ways that you can choose the transform. So what transform is the best in terms of compression? And generate the largest amount of zero copies, right? Generate the largest amount of zero copies. So let's pose this question this way, okay? Let's investigate this problem. Design the optimal linear transform, okay? Or in other words, amongst all the linear transform, among all the matrices that you can pick, which one should you choose? Which one is the best decorrelation, offering the best compression, okay? So the problem is this. So this is a formal problem statement. Okay? Start with an endpoint signal X. Okay? Y stands stationary and all that. Okay? Zero mean, Y stands stationary, random process. That's the only way we know how to model our signals. Okay? Given that endpoint signal X. find the set of orthonormal basis function phi such that the mean square error between the L point truncated representation. That means you throw away. You only keep L coefficient. You throw away the rest. Okay. See? So I only keep maybe the first L. Okay. The order is not that important. I don't mean that you all should always keep the one up front, but you can always permute it so that the guys who keep are up front, right? So let's say you permute and only keep the guys up front, throw away the rest. Okay. How do I pick phi such that the difference between this guy and the original signal in the mean square sense is minimum? Okay, so that's the problem statement. How do we solve this? Same idea as we have been doing before. We're going to try to write mean square error between x and x hat, and we're going to try to do some derivatives, right? And hopefully we're going to come up with the fix. Okay, so that's the overall game plan. So let's remind you that the orthonormal constraint means this. The dot product between phi I and phi j is just delta I minus j, orthonormal, okay? And then I also remind you that the autocorrelation matrix of the signal is defined as this, which is just the expectation of the outer product of x and x transpose. Okay, so this guy is just the expectations of x times x transpose, where x is a column vector, okay? X is a column vector. So, how do we start? First, MSE. Okay? MSE is the expectations of x minus x hat, L2 norm squared. Agree? Okay? And then we try, what is x? X is a linear combination of the phi. Okay? X is a linear combination of the phi. So I can write x as yi phi, and here I go from 0 to n minus 1. Means that I have everything. I keep every coefficient. Okay? But x hat is the truncation, right? That means you throw away. You only keep the first L guys. And L obviously is much smaller than n. Okay? You only keep a few coefficients. Okay? So x hat is just a summation I from 0 to L minus 1 yi phi squared. Okay? Now, so whatever they share, okay, give me 0. Okay? But whatever I throw away is this. These are the guys that I throw away, right? These are the errors. See? I throw away the guys from L to n minus 1. These are the guys that I throw away. I should minimize this expectation. Minimize this expectation, right? So this is the next step. So instead of writing it as L2 norm, I will convert it to inner product. Okay? Convert it to inner product, and I can write this as the expectation of these two inner product of these two guys. This dot product with itself. Okay? And then so this is the same as doing expectations of summation of these guys times the summation of these guys. Okay? There's no problem. It's just standard manipulations of matrix and vectors. Okay? So next, I'm going to be able to, okay, since the phi I dot product of phi j give me delta I minus j, what I pick up is only the guys in the diagonal. Right? Because if you're off diagonal, you automatically get eliminated. Okay, so I only pick up the guy in the diagonal, which means that it's only the yi. Okay, so this is exactly what we expect. Okay, the error, the mean square error, is simply the energy of all the coefficients that you throw away. Right? We just show that the energy in the error in x is the same as the error in y, And in y, we're throwing these guys away. So that's the error that we make. So there's nothing surprising up to this point, okay? Now, next up, I'm going to represent the yi. Yi is pi transpose times x or x transpose times pi, okay? So I write this yi squared is this, okay? Distribute the expectation inside, and I have that. Okay, so after a lot of just basic vector matrix manipulations, I get my mean square error to be this. Can you recognize this? What is this? That's RXX. That's the autocorrelation matrix. That's the autocorrelation matrix. So that turns out to be RXX times pi transpose times pi. Okay, and we want this to be minimum. Okay, so another reminder. If I have RXX times E equal to lambda times E, then lambda is the eigenvalue of RXX, and E is the eigenvectors of RXX. Okay? I will need that. So the question becomes this. Okay? Minimizing the mean square error, which we manipulate to show that is equal to this. Okay? With respect to these constraints, we need the orthonormal constraints, right? Those are the only constraints that we need to do. So what is the solution? What type of approach should we do? I'm looking for the magic keyword. For what is the magic keyword for constraint optimizations? Lagrangian, right? We need the Lagrangian, right? So without the constraint, you just take derivative like we did before. But with the constraint, you need to introduce the lambda, okay, the Lagrangian, and then take into account the phi, okay? So the Lagrange multiplier technique is this. Instead of, so minimize the mean square error, and you have to take into account the constraint, okay? So that adds the second part to the equation, okay? Now, I'm taking the derivative with respect to a vector. Okay? So, I need some of these basis manipulations. The derivative with respect to the vector v of u transpose times v is just u itself. The derivative with respect to the vectors v of v transpose times av is equal to 2av. Just like when you do v squared in scalar form. Okay? Now, if you feel a little lost here, don't worry about it. Go back to the basic matrix vectors textbook and try to verify these step by step. Okay? Since we don't have much time left. So this is what we have to do. Okay? This is eigenvectors of your set based on that RXX matrix, autocorrelation matrix. Choose the basis function as the eigenvectors, okay? And you have n of them. You have n basis functions, okay? And then send the larger eigenvalues first, because that will minimize the mean square errors. Okay? This is very important. Okay? So let's step back. Okay? If you're lost within somewhere between point 1 and point n here, don't worry about it. Okay? Let's step back and take a look at this very nice equation. Okay? What it's saying is that in order to design the optimal transform, you should pick all your basis function to be eigenvectors of RXX. Okay? That's all it's trying to say. Pick your eigenvectors as the basis function. Okay? And if you pick the eigenvectors as the basis functions, the transform coefficients will turn out to be eigenvalues. Okay? Send the eigenvalues over. Send the eigenvalues over. Okay? And you should, the larger guy is obviously a lot more important than the smaller guy because of this property. Okay? The errors is a summation of all the eigenvalues that you throw away. So you should throw away the small one and send the large one. Okay? That's all there is to it. Now, in practice, we actually, I don't know if you guys know the eigenphase techniques that people at MIT use for face recognition. They actually use the same techniques. Okay, every face they compute the RXX of they compute a few large eigen values of each of the face, and they compare faces on the eigenspace. So that's called eigenphase. Okay, they only compare the first few coefficients. Okay, and if it's matched, the first few coefficients should match well. Okay, so for example, female and male. Female has a different set of eigenvalues, and male has a different set of eigenvalues. Hopefully, right? And that's how they tell male female apart. Okay, for example. So people actually use this a lot in practice. Now, let's think about the problem that we have to face. We managed to prove a nice theorem. By the way, this problem is formally posed also in the 1950s. Okay, along with Loimax, along with entropy coding techniques. Okay, so we know this for a long time. Okay, now the next question is, can we actually use this in practice? Okay, anybody has any problem with this?
The computation is very complicated.
Right. So what happens at the encoder? That doesn't seem to be any problem, right? Computing the eigenvectors, eigenvalues. Okay, computationally expensive, but it can be manageable. Okay. Let's think about the decoder. What does the decoder need to reconstruct? It has to know what basis function being used in the encoder, right? How do you send it over?
You have to send over the basic function.
Okay, you have to send over the basis function with the signal. Is there anything wrong with that?
No.
What is the size of the basis function? Same size as your original signals, right? How many basis functions do you have? N of them, right? Okay, that wash out your compression. Okay, right? You have to send the basis function along with the filter transform coefficients, right? For the decoder to be able to decode. So that just wipe out your compression. Okay? And then each of does your basis function change?
No. Yes.
Yes, because it's dependent on the signal.
Okay.
It's dependent on the signals, right? Every signal has a different RXX. Okay? And so the decoder doesn't know. Okay? Now if we use Fourier transform, does the decoder know? Yes. The Fourier transform is fixed, right? Okay, it's E, J, omega, whatever. So the decoder knows exactly what the encoder used. So that is a problem. This is optimal, but it has no practical value whatsoever. It has no practical value whatsoever. Okay, we learned good lesson from it, but it doesn't have any practical values. Okay, signal dependent means first of all it's computationally expensive, and the main problem is this: you need to solve this encoder-decoder communications. You need to use the same set of basis functions. So somehow you have to communicate the basis function over, and that is costly. It's just sending the raw signal, right? N times. So completely useless from that aspect. So how do we solve this practical? Okay, now that we learned this nice lesson, we learned a very powerful lesson. We should design a good transform is the set of eigenvectors, and but in order to solve this problem, we have to assume a reasonable signal model. Okay, if we have a reasonable signal model, we can compute the RXX in advance, and it stay the same, right? We send that RXX over just one time, right? And then we're done. We establish the encoder-decoder communication Okay? And then after that, we just use that same set of basis functions. Okay? So in practice, what people did is assume a reasonable signal model, for example, the AR1 model that we played around yesterday. Okay? There, you know exactly how our x-axis look like. And you can always compute. You can always compute the eigenvectors. Okay? And then you store it at both places. You store it at the encoder, you store it at the decoder, using the same set. Okay? So the problem is it can only work well if your signal happens to match a signal model. If your signal doesn't match a signal model, then you are suboptimal. Okay? That's the way it is. So now it turns out that a good KLT approximation for a smooth signals model is the DCT, discrete cosine transform. Okay? And hopefully today, in our MATLAB demos and assignments, we're going to be able to confirm this. Okay? We're going to take a nice RxX, okay? Compute the eigenvectors of that RxX, and you'll be able to observe that it's very close to the basis function of the DCT. Okay? So then, that's why that explains why the DCT is very dominant in image and video coding. Okay, so the summary, optimal transform comes from eigenvectors, eigenvalues, decomposition, okay? And the KLT is nothing more than a set of eigenvectors of the input autocorrelation matrix. The correlation matrix RxX, okay? Now, to construct a good basis means you have to come up with a good signal models and try to use the same set of basis function on both sides. Okay? So one of those good models is the AR1 model that we used before, and it turns out for that AR1 model that we use, the DCT is a close approximation of the original of the KLT. And the DCT has many different types, okay? So this is quite similar to Fourier transform, right? But you notice that there's no EJ omega anymore, okay? So we only have the cosine part, we don't have the sine part. And it's real, it's not complex, okay? And it's not just the real part of the Fourier transform. It's not the real part of the Fourier transform. It's a little bit more than that. Okay, so this is the type 2 DCT. It's the type of transform being used in JPEG and MPEG. Okay, and this is the definition. Okay, so the type 2 DCT matrix is this. The index of the matrix is m and n, and if you substitute m and n in, m goes from 0 to m minus 1. So this is of size m. This matrix has size large m. Okay? You have different cosine being sampled at different locations. Okay? Furthermore, you have cosine of different frequency. Okay? So you can think of m here as taking care of the frequency. So having larger m means you have cosine that oscillate more. Okay? So this, typically, the basis function of this guy, oh, I'm going to have it in the next slide. Okay. So the basis function look like this. If I plot the basis function, it will look something like this. Okay? By increasing m, you increase in frequency. Okay? And this n represent the index in the sampling in time of these cosines. Okay? So this direction is m, this direction is m. It's an 8 by 8 or m by m, large m by large m transform. JPEG use 8. Pick m as 8. And a block has 64 samples of pixels grouped together, okay, being processed together using this 2D DCT transform. And typically, the behavior is like this. Okay, this is called DC, or the average of the block. Okay, Y average. The first basis function is all frequency zero. Okay, all the samples get weighted the same way. Okay, and if you do it all the columns and then all the rows, it just give you the average of the block, right? Which is nice. Okay, at least you know the block is dark or bright, or okay, but it doesn't have any information about how the block behaves. Okay, it's just the average of all the pixels in the block, and that's the DC coefficient right here. Now all the low frequency guys will be right here, right? The guys that has more little m will be right here, and then all the high frequency guys will be right here. The middle frequency guys will be right here. Okay. It turns out that all the horizontal edges will be somewhere here, and all the vertical edges will be somewhere here. Okay. Why is it vertical here but not horizontal here? You can think of these bases as the way that you compute the coefficients by doing the convolution of the bases, right? So if you have edge at the vertical direction, and you do convolution across, you pick up large energies, right? So that's why they are up here. But if you have a lot of horizontal edges, and you do convolution this way, you pick up a lot of energy here. Okay? So in the transform coefficients, it's reversed, right? A lot of horizontal energy will go here, a lot of vertical energy will go here, and the typically behavior of a block is that most of the time you have large coefficients here, and a lot of zero or small coefficients over here. That's why you can throw them away. You only keep a few guys up there. Usually we always keep DC, right? Right? The average is very important. The average is very important, right? It tells you that the block is black or white or whatever. That's the fundamental information of a block. And we always keep DC, and then we keep a few more low frequency coefficients. Okay. Now, questions. If I have a block that has no variation, okay? For example, all gray, okay? Or all black or all white. I feed it through the DCT, what do I get?
Only DC.
Only DC. Why?
Because of the frequency.
Right, because when you do convolution of a constant sequence with all these variations, they turn out to give you zero order. Okay, so if the block has no variation, you only pick up one guy, which is the DC right here. Everything else will be all zero. So that's a tremendous amount of compression, right? You will keep one out of what? 64. You keep one out of 64 and you get perfect reconstruction. You keep one out of 64, but you get perfect reconstruction. Now, in natural images, a lot of times we encounter this situation, right? I take a digital camera, I take a snapshot maybe right here. Guess how the wall behaves? Constant, right? Constant. So in that case, we have 64:1 compression at least, at the minimum, okay? And we have perfect reconstruction. Okay? So that's how we do compressions in practice. Now, there are several interesting properties about the DCT, and some of them I asked you to prove, okay, in today's assignment, written assignment. The first interesting properties is the symmetry, okay? And so I have some of the sketchy proof right here, and I want you to expand on it, okay? There's another nice properties regarding the recursive properties of the DCT. And we encountered this problem before with the DFT, right? How do people get the fast Fourier transform? People get FFT based on the factorization into smaller guys, right? Instead of doing an n-point DFT, you do 2n/2, right? You do 2n over 2 DFT, and then you keep on breaking it down. The DCT also have some interesting properties, and you can show that in order to implement an m points DCT, you can do 2m over 2 points, okay? But one is type 2, one is type 4. The type is in the previous 2 slides, okay? Just different sampling. So that's another property that I want you to show, okay? So in a very high level diagram, we have something like this, okay? You take the difference, and then you take a smaller DCT here, another smaller DCT here. So that's another property. Now, this is a typical implementation in practice. People don't do matrix multiplications when we implement the DCT. We don't do matrix multiplication. Just like we don't do matrix multiplication when we have to take the DFT or something. We actually break it down into you probably recognize this, right? It looks like DCT, FFT style implementation, right? So you break the big matrix into smaller ones, okay? So this is a typical fast implementation of the DCT, and these C stand for cosine. So this is cosine of pi over 4, which is square root of 2 over 2. This is sine of pi over 4, which is square root of 2 over 2. This is cosine of 3 pi over 8. This is sine of 3 pi over 8. So on and so forth. So people actually do a lot of investigation and come up with factorizations of the DCT matrix like this. So this is pretty typical, and you can count that in order to implement this, you need about 13 multiplications and 29 additions per 8 input time. Okay? That's in 1D. Okay? If you do 2D, you need to do this on all the rows and then all the columns. So in 2D, it takes 16 times this operation. So you can quickly do multiplication, and that's only for an 8x8 block. So you can see that it's quite computationally intensive. Okay? Now, how do I do the DCT of an image? Okay? Typically, the image, like we saw yesterday, has large size, right? 512 by 512, 640 by 480, or even the small Q subframes is 176 by 144. Okay? And in practice, people break it into small blocks. Like in JPEG, 8x8 blocks, or also in MPEG, 8x8 blocks. Any idea why we pick 8? Why do we pick 8 instead of 7 or 9 or 13? Power of 2 is nice. Power of 2 gives you nice factorization. So that's one. But why not 16?
Because the extra memory.
Yes, implementation issues. Okay, because of implementation issues. And also, when you make the block larger, you lose the correlation within the block. So it turns out that 8 is a good trade-off between decorrelation properties, implementation cost, and so on and so forth. Okay, so that's why we picked 8. So in practice, we block our signal into smaller blocks. And for each of the blocks, we do a local transform. Okay? So this is the global viewpoint. This is the global viewpoint. And the matrix that allows you to map your entire signal X into the entire set of coefficients, maybe I should call them Y. Okay? Is this. It's a block diagonal matrix. Okay? Now, did we study wavelets? How does the wavelet matrix look like? Okay? Is wavelet matrix sparse with a lot of zeros? Like hard. Does it have a lot of zero? Yes, it has a lot of zero, right? Because the basis function is very short, right? 1 minus 1, 1, 1, 1 minus 1, right? So it's short, but it doesn't have this block diagonal. Okay, wavelets is based on iterations. Okay, So you take one level, and then you take all the low pass, then you iterate, right? So the wave overall transform matrix doesn't look anywhere close to this. It actually have a few longer basis function and a whole bunch of shorter basis functions. Okay, so this is totally different. Okay, this is very local. All right, so maybe I stop here. This is a good place, and we're gonna have.